Okay, so in the first part of this course, I am going to talk about the plactic monoid. And later on, I am going to talk about crystal operators on words. Now, all these ideas, like we have been looking at them from the point of view of Littleman's path models, but Littleman's path models were themselves inspired by classical work. So, some of the notable papers on this, there is a paper by Robinson in 1938, where he claims to give a proof of the Littlewood-Richardson rule. And in this he introduces certain, he basically introduces some operators and some correspondences. Schensted has a paper from 1961, and in this he introduces what is now called the Robinson-Schensted correspondence. And then Schützenberger, (1964). In this paper, he introduces the plactic monoid and jeu de taquin, and actually kind of completes Robinson's proof of the Littlewood-Richardson rule. And there is also a paper by Knuth in 1970, where he generalizes this Robinson-Schensted correspondence to what is now known as the Robinson-Schensted-Knuth correspondence. But underlying all these things is a very simple algebraic structure, which I will try to explain to you. It is called the plactic monoid. So here is the game though. So if you have a semi-standard Young tableau, say something like, I guess everybody knows what a semi-standard Young tableau is by now. So if you have a semi-standard Young tableau like this, you can associate to it a monomial. So we will assume that our language has a certain, we have numbers, we are using numbers from 1 to n. So let us say we are using numbers from 1 to 7, then you will have 7 variables x1, x2, x3, x4, x5, x6, x7, and the monomial that you will associate to this tableau is x1 squared, because there are 2 1s, x2 squared again because there are 2 2s, x3 squared, x4, x5, x6, x7, right. So this is called the weight of this tableau. Okay, so if this tableau is T, then this I will call the weight of T. And the Schur polynomial is defined as I will give all these things in more detail later on, but semi-standard Young tableau in n letters of shape lambda . This polynomial is also the character of the representation of GLN, polynomial representation of GLN corresponding to the partition lambda. So that is the context that you are more familiar with. But you can just think of it in very simple terms as a certain very special polynomial, which has been known for a long time, going back to Cauchy, etc. And it turns out that this polynomial is symmetric. You may have seen some reasons for this already, but the big problem was, okay, it was known that these polynomials form a basis for the ring of symmetric polynomials in n variables. If you take all partitions of the integer d, then these polynomials S lambda, as lambda runs over all partitions of d, would form a basis of symmetric polynomials. Lambda runs over all partitions of d with at most n parts. Let me just write that down. this is a basis of symmetric polynomials homogeneous of degree d in n variables. And so, if you take two of these polynomials and multiply it, say S mu and S nu, then this is again going to be a symmetric polynomial of some larger degree, the degree of mu plus the degree of nu. So, you can ask, how can I decompose it into the basis of symmetric polynomial degree, the sum of these degrees. So, there will be some coefficients as C lambda mu nu S lambda, and you can just take n very large, then these things will stabilize. So, we just assume that n is quite large for lambda and mu and nu. So, just take n to be larger than the sum of the size of mu and the size of nu. Then these things will stabilize. As you introduce more variables, it will not matter, and these things are called the Littlewood-Richardson coefficients. So, it turns out that these Schur polynomials are also characters of representation of a symmetric group, and this product operation on characters is the same as taking the tensor product of two representations. So, basically you are taking a representation symmetric group corresponding to mu, another representation corresponding to nu, you are taking that tensor product and asking how does it decompose into irreducibles, and or rather what is the multiplicity of a given irreducible in the tensor product. So, you know that these integers have to be non-negative. Yeah, general linear group. Sorry, general linear group, and so you want to know. So, these are non-negative because they are multiplicities. So, whenever you have non-negative integers, you ask, well, can you tell me some nice set whose elements they count, and the Littlewood-Richardson rule in some sense answers that question, and it is based very much on this notion of the plactic monoid. So, let us start. So, I am going to take as my alphabet. So, we are going to look at words in a certain alphabet. A word is just a string of symbols. So, like in computers we have words in the ASCII character set maybe, which includes spaces, punctuation and the letters. So, here we just take an alphabet which I will denote by a n to be just the symbols 1, 2 up to n. Okay, so, that is my alphabet, and this alphabet, a very important feature of this alphabet is that it is linearly ordered. 1 is less than or equal to 2 is less than or equal to 3 and so on, and this is something that we are going to make use of a lot. And a word in the alphabet a n is just a sequence of the form a 1, a 2, a l, where each a I belongs to a n, and we will say that the length of this word is the number of symbols in this. So, these symbols could be repeated, there is no condition, they are just independently chosen. So, and there is an algebraic operation on words, you can concatenate them. So, we will denote a n star to be the monoid of words in a n, where the multiplication in the monoid is defined by concatenation of two words. So, you take the first word and write the next, if you want to find out W 1, W 2, you write W 1 and then write W 2 to the right of it. So, that is the word monoid. Okay, and we will look at some special kinds of words. So, there are words which are called rows. They somehow correspond to rows in a semi-standard Young tableau, like 1, 1, 2, 3, 7, 2, 3, 4, 5, 6. So a word is called a row if let us say W equals A1 AL is called a row if A1 is less than or equal to A2. If these letters are simply in weakly increasing order. So, for example, so we will say R L A n equals the set of all rows in A n of length L. So, what is the cardinality of this set? Okay, so it will take you back to a combinatorics exercise from college or high school, right? Yeah, so it's n plus L minus 1 choose L. And similarly, we have columns. So, W in A star, A n star is called a column if W is of the form A1, A2, AL with. So, it should look like a column of a tableau, but the French actually wrote the tableau the other way around with the So, this is I guess it is called English notation. It is not clear what the English did here, but so the French would write it like this, which is much more natural. And then when you look at these columns of this, what they are is they are strictly decreasing. And CLAN is the set of all columns in AN of length L. And how many of these are there? Just n choose L, right, because you just choose which letters will appear in your column and they have to be in that order. Okay, we can also talk about the weight of a word. Words have weight. So we will have this map from A n star to integer polynomials in the variables x1, x2, xn, which I will call the weight function. So, V of A1, A2, AK or AL maybe is just XA1, XA2, XAN. So, you just the power of xi is the number of times that I occurs in the word. Okay, that is what this formula is saying. So, already you can say something interesting about symmetric functions. So, you define Ek x1 up to xn as sum over W in R HK R K A N. what is this? So, this is going to be a sum of all monomials of total degree. So, if this word has length L, then the degree of this monomial is L. And so, here we are just taking all rows of length L. So, of course, this polynomial will be homogeneous of degree k here, not L, and it is going to have all possible monomials of degree k, each one written down once. This is called the complete symmetric polynomial of degree k. And E k, similarly you can guess here you will only get monomials where all the variables are distinct. Okay, so, this is called the elementary symmetric. So, already with just these very simple definitions, you get some interesting symmetric polynomials. And it turns out that these two families of symmetric polynomials, they generate the algebra of symmetric polynomials. Okay, so, every symmetric polynomial can be written uniquely, in fact, as a polynomial in either this family H k or in this family E k. So, those are called the fundamental theorems of symmetric polynomials, which I am sure many of you have seen. Okay, so, in what we will be doing is, we will be trying to look at Tableau associated to words, and we will also be thinking of Tableau themselves as words. Okay, so, in order to do this, let us just look at certain canonical decompositions of Tableau and see how we can canonical decomposition of words and see how we can define Tableau and so on, just in this theory of words. No. So, let us just look at an example. So, so let us look at n equals 4 and k equals 2. So, E2 of x1, x2, x3, x4, this will have a lot of terms. It will have x1 squared plus x2 squared, x4 squared. Then it will have things like x1, x2 and so on. Huh? Oh, sorry, H2. Whereas E2 will only have okay, so it will have all distinct variables and it will also have these things. So, this part is E2 and these things do not occur in E2. So, they are actually completely different families except for k equals 1 when they are both equal. Okay, so, if you look at degree 3, then you will have terms like x1 squared x2 in H, where H3, but in E3 you will only be allowed to have terms of the form xi, xj, xk, where I, j, k are all different. No, the cardinalities are different. What do you mean cardinalities? No. So, this RL is the number of sub multisets of size L in a set of size n. So, I usually denote that by n choose L. So, these are sub multisets. and if you want CL AN, then it is just subsets. Okay, and by the way, this is n plus L minus 1, choose L or n over L. So, there is a cute proof of this fact. Some people like to use stars and bars, but there is a much nicer proof, and that is that if you have a row, right, A1 less than or equal to A2 less than or equal to AN, then you just say AL, right, of length L, then you just replace it by A1 A2 plus 1 A3 plus 2 AL plus L minus 1. These are clearly all distinct, right? And similarly, if you have and there are this will be here we have this condition that this should be less than or equal to n, but here the condition becomes that this should be less than or equal to n plus L minus 1. So, this is a set of distinct elements between 1 and n plus L minus 1. So, the number of such sequences is n plus L minus 1 choose L, which is therefore this is a bijection. Given such a distinct set, you can again subtract 0 1 up to L minus 1 and come back to sub multisets. So, this kind of motif appears a lot in even in Cauchy's definition of symmetric functions. This appears, and whenever you work with partitions, there are many situations where you will take a partition and then you will start adding these numbers 0 to L minus 1 to them and get distinct partitions. So, okay. Yeah, lambda, and yeah. So, if this is a partition lambda, then this is the partition lambda plus rho in the language of root systems and so on. Yeah.
Since you are on it, I also mentioned that 1 plus 2 plus 3 till L minus 1 is also the triangular number. So, this is going to be the proof that I have given more about.
Okay, so yeah, so here the size of this is the size of this plus a triangular number, and this will be used tomorrow in Vishwanath's lecture. Okay, good. So, I have paved the way for your proof. Okay. So, okay, so now let's look at words and try to break them down in various ways. So, there are two decomposition. One is called the row decomposition and the other is called the column decomposition. So, the row decomposition is a decomposition of form. A word W will be written in the form UL. Here the indexing goes backwards U1, where so this is called a row decomposition. The row decomposition of W. If firstly Ui is a row for each I, and Ui minus 1 is not a row. So, what I am doing is I am taking this word and breaking it up. I am looking at the, I will go to read it till there is a, as long as the letters are weakly increasing. The first time I get a drop, I will cut it and I will call that first part UL. Then again, well, I do not know what L is right now. So, then I will take the second weakly increasing, and then when there is a drop, I will cut it again. Let me show you an example. So, let us look at this word 4, 2, 5, 6, 1, 1, 3, 6, 6. So, what is its row decomposition? So, let us try to read it. 4, whoops, it already drops here. So, let us cut it here. 2, 5, 6, that is weakly increasing, but then it drops. So, this is the row decomposition. This is U 3, U 2, U 1. And similarly, there is a column decomposition. W equals V1, V2, VL, where each Vi is a column. So, is so right now my choice of choosing backward indices here and forward indices here may just seem like an eccentricity. Anyway, it does not matter at this point. If, well, same as here, Vi is a column for each I, and Vi plus 1 is not a column. Actually, is this right, or do I want? Yeah, so let's just take it like this. So, let's look at an example. Let's take W to be the word 4, 2, 1, 5, 1, 6, 3, 6, 6. So, what do? I start reading it, and then every time I see a weak increase, right, I cut it off. So, 4, 2, 1 nicely decreasing, and then 5 it increases. So, I better cut it off here. 5, 1 nicely decreasing, and then it increases here 6, 6, 3, that is good. 6, 6, 6 is not allowed. I need a strict decrease, it is not a column. So, this is V1, V2, V3, V4, V5. This is the column decomposition. Okay, and I will just write down a certain tableau here. So, this tableau kind of unifies these two pictures. Well, these are very special words. Okay, these words are what are called tableaus and dual tableaus. But if you read along bottom to top along the columns, you get this, and if you read bottom to top along the rows, you get this. Okay, just observe that for now though. Yeah. Yes, yes, you need a condition. So, I am coming to those conditions. So, not all words are tableau, and what makes a word a tableau? Every word has a row decomposition, every word has a column decomposition. So, there is a relation called row dominance. So, suppose I have a row U and another row V, we say that V dominates U if one, length of V is less than or equal to length of U, and 2, Bi is strictly greater than Ai for I equals 1 to length of V. So, that means if I write U and then I write V below it, then it looks something like this. So, I will have up to AM, and this is where B will end, and then A will go on maybe, and the dominance condition says that this B1 should be strictly greater than B2 A1, this B2 should be strictly greater than, and so on. And of course, we already know these things because they are rows. So, from this we will get a condition for Tableau. So, we will write here V dominates U like this. So, now we can define a Tableau. If its row decomposition has the property UL minus 1 U1 satisfies UL dominates UL minus 1 dominates. Okay, so this word is a Tableau because you break it up, take its row decomposition, write those rows next to each other in a left justified manner below each other, and what you see is that the columns are strictly increasing. So, Tableau word is clearly in bijection, the set of Tableau words is clearly in bijection with the set of semi standard Young Tableau, and the shape. So, this only applies to, well, the shape of W is this partition length of U1, length of U2. Remember, in this dominance relation, the thing that dominates is shorter or not, at least not longer than that. So, this is going to be a partition. And there is a dual notion called column dominance, which allows you to define what are called dual tableau. We will say that, so suppose we have columns, so these are rows. Let us say these are columns, we will say that V dominates U if length of V is less than or equal to length of U and bi, now I will just say it is greater than or equal to ai. And we say that W in A n star is a dual tableau. Oh, by the way, here, okay, yeah. Let's not get distracted. Huh? Sorry? Oh yeah, sorry, L M. So, so I'm going to say that this second column here dominates the first column. Okay, so. So, we will write here V, and I need some other symbol. Sorry, I can't hear you. So it's, you know what a monoid is? It's algebraic structure where you have one binary operation that is associative. That's it, right? And so it's like a group, but you don't have inverses. Okay, and maybe you're supposed to have an identity. So you're also supposed to have an identity. So if you take words, then the binary operation on two words is to just write the first word and write the other word next to it. So that's a longer word whose length is the sum of the lengths of these words. And this you can check gives the set of all words the structure of a monoid. Okay, the identity is the empty word with no letters at all, a word of length 0. And if you multiply it on the left or right by the empty word, you get back the word. So, it is an identity. So, that is the monoid structure. Right now, we are using the monoid structure in the sense that when I am saying that a word decomposes into parts, this is really saying that I am cutting the word in pieces. So, in some sense I am saying it is a product in the monoid. It's we are using the monoid structure all the time here. But maybe you do not need to really think of it that way, where intuitively also when you have a word, you just cut it into pieces and talk about it. But later when I introduce the practic monoid, I think the monoid structure will be more consciously used. Okay, right now it is just words are sequences of letters, monoid structure is just concatenate them. So, there's some there's slightly different, yeah. So monoid monoid is a semi group with an identity element. That's another way of thinking about it. Yeah. No, they are already columns. So let us look at this example. 421 516366. Okay, so V1 is 421, V2 is 52. So here I have written 421. Oops, yeah, there is something wrong here. 51. Yeah. So damn it. There's a problem here. I need to write them backwards. Yeah. So, okay. So you now you usually you write columns from bottom to top. If you're French, you write them from top to bottom. And so if you take this word W, then what is its column decomposition? Its column decomposition is 4 to 1. So I'll write them from bottom to top. 5 1, I'll write it from bottom to top, but aligned on the top. And 6 3, 6 and 6. And then I'm saying that each element of the second column is greater than or equal to the corresponding element of the first column. I am sorry, I made a mistake here. These are to be written backwards. It is so in my notes, but I forgot to write it on the board that way. Yeah.
So your second condition must be
I equals 1 to m. Yeah. So let me write it like this. M is less than or equal to L. And the shape of W as a column tableau is which is again a partition. Yeah. So we'll use some notation here. We'll say tab lambda W, no tab lambda an to be the set of all tableau of shape lambda in the alphabet an. Yeah. Oh, it's the other way around. Yeah, yeah. Sorry, it's again. Thank you. I think I'm getting confused by my own notation here. Thanks. So example, right? Well, the example is here. 4 2 1 5 1 6 3 6 6. This is a dual tableau. So this word is a tableau. This word is a dual tableau. So I'll use the notation tab lambda an to denote the set of all tableau words of shape lambda. In the alphabet an, and I'll use tab star lambda or tab prime, maybe tab star lambda to be the set of all sorry, the lambda goes down and the an comes here. I need to know what the alphabet is also, right? The set depends on how many letters in an. Of shape lambda in an star. Okay, so we get two expressions for Schur functions in terms of, I mean these two sets are equinumerous because of this way of drawing them that I showed you. They both give rise to semi-standard Young tableau. Right. And this bijection of course preserves preserves weights. The number of ones, number of twos are the same. So, what we have is both are equinumerous with semi-standard Young tableau of shape lambda in n letters. Yep, sorry. Yeah, let me get back to you. Yeah, so I need to explain this. Sorry, I jumped the gun here. There's one more subtlety. So, yeah. So now let's talk about the conjugate of a partition. So if lambda is a partition, then you can draw its Young diagram. It's the set of all pairs I j where so let's say this partition is lambda 1, let's say it has L parts lambda 1 to lambda L, so then it's 1 less than or I less than or equal to L and 1 less than or equal to j less than or equal to lambda I. It's the set of all such pairs, and we'll usually plot these points the way we write down matrix entries. I j represents the point in the ith row and jth column. So, if you draw a small box for each of the things, so let's look at this partition lambda equals 6, 5, 3, 3, then I'll be looking at 6 boxes in the first row, 5 boxes in the second row, 3 boxes. Okay, you could just think of this as the point 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 3, 1, 3, 2, 3, 3, 4, 1, 4, 2, 4, 3. In this thing of points, we draw boxes because ultimately we would like to put numbers inside these, right. And lambda conjugate is the diagram obtained by reflecting this about the line I equals j. So, y of lambda prime equals reflection of y lambda about the line I equals j. So, this is the conjugate of a partition. And so now, I had this thing here. 4, 2, 1. Six, 3, 6, 6. So, so this tableau has shape 1, 2, 3, 4, 5, 5, 3, 1, right. So, what is the conjugate of 5, 3, 1? 3, 2, 2, 1, 1. And this is an involution 3, 2, 2, 1, 1, conjugate is 5, 3, 1. So, what we have is if you are given a tableau of shape lambda in A n, it just gives you rise to a semi-standard Young tableau of shape lambda with numbers 1 to n filled into it. On the other hand, if you have a dual tableau of shape lambda in A n, it gives of shape lambda prime in A n, then it gives you a tableau of shape, a semi-standard Young tableau of shape lambda in A n by the method of writing the columns from bottom to top aligned on top. Okay, here you write the rows from left to right aligned on the left. So, these are equinumerous things, and we get two different expressions for the Schur function in terms of these things. So, I told you earlier that S lambda of x 1 x n but this can be written as or as W belongs to tab star lambda prime a n. So, these are two ways of writing the Schur function in different types of words. Yeah. No, if you conjugate at W, it just reverses the order of the lambda plus rho minus rho. Lambda plus, you mean W dot lambda? No, I don't think so. W naught is, so this is more like a, so this, okay, let me not say anything, but it's so lambda prime is yeah. So, for example, if lambda is just a row, that is a young one part partition, then lambda prime is a single column partition. So, they do not seem to be particularly related in the while group or anything. Okay. Okay, so now I will define the insertion algorithm. So, this is motivated by, so Schensted, among the people I listed in the beginning, Robinson, Schensted, Schutzenberger, and maybe I should have mentioned Lasko and Schutzenberger working together, and Knuth, most of them would be considered computer scientists, except Robinson. Well, Schensted was actually a physicist and a game designer. He designed board games. So, but the paper that he wrote, which I mentioned, is essentially an algorithmic paper. So, the problem is this: you are given a long word and you are only allowed to read it once. Okay, it is very long, you can't, and so you just walk along and you get to read the letters one by one, and you can write down stuff in your notebook, but you are not allowed to come back and read it again. Once you have read it, it is finished, and your goal is to find the length of the longest increasing subword. Okay, so, this alphabet that we have 1 to n, it is an ordered alphabet. So, I want to find the length of the longest increasing subword. And so, Schensted starts off his paper by saying, okay, let us try to find an algorithm for this. So, let us see how we can do this. So, I am given some long word, let us say we have a 5-letter alphabet, and I am given a word 1, 2, 1, 5, 4, 2, 3, 1, 5, 2, 4, 5, 1, 3. Okay, so, I am given this word, not very long, but long enough for hand calculations. And now I want to find the longest increasing subword, and once I read something, it's gone. It will be rubbed off the board or whatever, you can't store it. So, so find the longest increasing subword. Some of you probably have the answer already. Any answers? Yeah, and there is one of length 5. Okay, maybe this was maybe not a great example. But anyway, maybe I should remove some things. Let's remove this 5. So then 1, 2, 3, 5. So maybe this is better. I mean, I could work with the other one also, but. Okay, so let's read this and let's keep track of. So I claim that you basically only need to keep track of one thing. The thing that you need to keep track of is for each I, whether you have observed an increasing subword of length I. Okay, that of course you need to keep. Oh yeah, okay, good point. So if W is A1, A2, AL, then a subword of W is a word of the form AI1, AI2, AIK, where I1 is less than I2 is less than IK. Sorry, yeah, this should be less than or equal to L, and this should be greater than 1. But these have to be distinct, you cannot repeat something. Okay, so idea behind the algorithm is the following. So firstly, for each j, you need to know whether you have observed an increasing subword of length j, but also you need to keep track of what is the least last letter of all the increasing subwords of length j. Okay, so for each j, keep track of the least last letter of when I say increasing subword, I mean row subword, right, of all row subwords of length j. Now, my claim is that if you keep track of this, then at each stage when you read a new letter, you can just update this table of data and move on to the next step. And in the end, what you would have done is for each j, you would have figured out what is the least last letter of all row subwords of length j, and the longest j for which such a subword exists would be the length of the longest increasing subword. Okay, so here what I mean is you keep track if it exists. If it does not exist, you should know it does not exist. Okay, so let us look at this word. So I start reading from here. So I have this 1. Okay, so I have an increasing subword of length 1 till now, right, and its least last letter is 1. Then I have 2. Okay, so I have an increasing subword, a row subword of length 2, and I have a row subword of length 1. For the rows, I have a row length 1 which ends in 1. This is the least last letter of row subword of length 1. This is the least last letter of a row subword of length 2. Okay, so we will keep it in this form. And now 1 again comes in. Okay, how does this change my data? So, I know that there exists a word of length 1 with last letter 1. So, I can just tag this 1 to the end of it, and I can actually get a word of length 2 with last letter 1. So, I have actually taken this thing and I have replaced it by a 1 after this word came in. Yeah, weakly. So, let me say row subwords. Yeah. And so, there was a 2 here, and to be somewhat dramatic, I will throw out the 2. Okay, just to remember that, okay, I threw out something. Now, what is next? 5. Okay, so I have an increasing subword of length 2. When I say increasing, now I mean weakly increasing, of length 2, which ends with 1. So, I can definitely tag a 5 to the end of it, and I will get an increasing subword of length 3 ending in 5, and I can't do better than 5 for a subword of length 3. Okay, but for a subword of length 2, I still have 1 and 1. So, I put a 5 here, and nothing is thrown out at this stage. Now, 4 comes in. So, I can improve this 5 to a 4 now, because I had a subword of length 2 ending with 1. So, I can tag the 4 to the end of it. So, I have improved this 5 to a 4. So, I will throw out this 5 and put in a 4 here. And now, I go to the 2. What should I do with this 2? Well, I can improve the subword of length 3 again, right? And I can't get a subword of length 4, because 4 was the longest So, I will throw out this 4, and I will put this 2 in here. Now, I have a 3. So, I can just tag it on at the end and improve my longest subword, right? So, you get the hang of it. Now, what do I do? Whom do I throw out? I throw out the 2, excellent, and I replace it by a 1. Then I have a 5. I do not throw out anybody, I put the 5 here. Then I have a 2. So, I throw out the 3. And I put in the 2, then I have a 4, so I throw out the 5 and I put in the 4, then I have a 1, so I throw out this 2 and I put in a 1, and then I have another 1, so I throw out this 4 and put in a 1, and then I have a 3. So, what this says is, I have a 1, 2, 3, 4, 5, 6, what? Yeah, so I have a weakly increasing row subword of length 6, I am allowed to repeat, right. So, weakly increasing, and in fact, I can find one that ends with 3. In fact, it is easy to find, it is just 1, 1, 1, 1, 1, 3. In this case, it turns out it is the same as the word here, but it is not so in general. Okay, so this was Shensted's algorithm. You start with a word and you just keep track of this in the form of a table like this, where you just list the least last letter of a row subword of length j for each j for which such a subword exists. Okay. Yeah, it may not always give a subword. The order in which these things were put were not necessarily left to right. So yeah, this random example is too simple. It somehow has all these ones, but we can continue this process. So now we have this set of discarded letters. Notice that there is no 1 in this discard. You never discard a 1. Okay, so just for fun, let us ask what is the longest increasing subword over here. now I am just doing it for fun. So now we are good at it, right? We will just practice. So we have 2, 5, then we put a 4, so the 5 comes out, then the 2 comes in and the 4 comes out, then the 3 comes in, then the 5 comes in, then the 2 comes in, but the 3 goes out, and then the 4 comes in and the 5 goes out. I hope I did it right. So I will write it like this, 1, 1, 1. And now I have this 5, 4, 3, 5. So 5 first, then the 4 comes in and the 5 goes out, then the 3 comes in and the 4 goes out, and then the 5 comes in. And now I have this word 5, 4, and the 4 pushes the 5 out, and then finally I have the word only 5, and I write it like this. So what has happened is I started with a random word here, and by using this Shensted's algorithm, I used it once to find the longest increasing subword. Yeah. Yeah, thanks. I repeatedly used it and I got something which, in this case at least, it looks like a tableau, right? And Schensted observed that it will always give you a semi-standard Young tableau. And you could ask, well, what is the shape of this tableau? What is the significance that this shape has? So that was a question that was answered by Curtis Green. So we'll come to that in a second. But this first row is its length is the length of the longest weakly increasing subword of the word W that you started with. Okay, so this motivates this first algorithm, which I will call row insertion algorithm. So we used this algorithm at every stage of implementing Shensted's algorithm. So what did we have? At each stage of Shensted's algorithm, we had a row U and a letter A, right? And what did we do? We took this row U and we tried to insert this letter A. And one of two things happened. Either this letter U came to sit comfortably to the right of A, or this U replaced some letter in A which then got bumped out, right, which we threw out. So there were two cases, one where we just appended A to the end, and the other where we threw out A prime and we modified, replaced one of the letters of U by A. So I'll denote this by empty and U, nothing was thrown out. So this algorithm can be thought of as R-ins U comma A is equal to, okay, so let's firstly say U is A1, A2, AL, then we will say that this is equal to U phi comma UA if AL is less than or equal to A, right. And the other case is we should throw out something AI comma, and then we will replace but what is the condition on this I? How do we locate the guy that we replace? So, what we were doing is we were looking for the leftmost entry that is strictly greater than A, where I is equal to minimum of j such that A is strictly less than Aj. So, this is called Shensted's row insertion algorithm.
This algorithm for the longest subword,
Huh.
if we want the subword of a particular length,
You will know what its least last letter is, that is all. Yeah. So, that is the row insertion algorithm. And dually there is this thing called the column insertion algorithm. So, we have a column U, a letter A, and now what we do is column insertion is done like this. This I don't know, I get confused with this left and right and rows and columns, but yeah. So, this is you maybe during AL, yes, this is AL. So, I will call it so it goes in the opposite direction. So, let us say U is A1 AL. So, what should be the condition here? I want this to be a column. So, I need that A is strictly greater than A1. And otherwise, I will bump out something. So, I will look at this A1 AI minus 1 AI plus 1 AL comma AI, where what should I look for now? So, I want this to be a column, right. So, I want this letter which I am throwing out should be the last letter that is greater than or equal to A. Because even if it is equal to A, I cannot put this to the right of that letter, because it won't be strictly decreasing, right. So, let me just show you an example. So, suppose we take 7, 8, 7, 5, 3, 2, 2, 1 and say I have to no, I can't take 2, 2, 1, 2, 1, it has to be a column, and say I want to column insert a 3. then it should push out the 3, right. Also if I column insert a 4, that would also push out the 3. No, in this case I want the largest first letter. So, you can work it out. So, what the analog of Schensted algorithm is to keep track of the largest first letter of a column subword. If I do 3 also, it is 8. So, this and then what gets bumped out is the 3. So, I equals max j such that A j is greater than or equal to what? Let us do an example. Okay. So, let us take those 2 words I had earlier and do this. So, my favorite 2 words. So, let us take no. So, this should be A j greater than or equal to A. A j, wait a sec. So, if A is greater than all these, then it just goes on the left, right. If not, then some of these things are greater than or equal to A, and I look at the last one. So, like here, oh, so should it be min j such that yeah, but I want to replace this no, it should be a min. Yeah, maybe that's the okay. Let me see how it is in my notes. So, in my notes I have this. Okay, so let me just see. So, I want to keep track of the largest first letter. So, I have this thing and now I have a 4 coming in from the left, and I want to keep track of the not the largest, no, the least first letter of a column. I want to keep track of the least first letter of a column. So, yeah, so the 5 goes out, you are right. So, the 4 will come in here and the 5 will come out. And if I have a 3, then the 3 will go in here and the 3 will come out. So, So, this makes sense, right. So, it should be min j such that aj is greater than or equal to a. Max, sorry, max, as written earlier. I just made a mistake here. So, this is okay if I say max j such that aj is greater than. So, this is the last one that is greater than or equal to 3, and here this 3 is the last one that is greater than or equal to 3 when I am inserting 3. Yep. So, let me write these examples properly since I have created so much confusion. This is the correct answer, then this is the correct definition. Okay. So, now we can talk about row insertion into a tableau. So, suppose we have a tableau W, then I want to talk about row insertion. So, we will write this as this, and this will be a new tableau called W prime. Okay, and I will explain to you how to do this. You already know, I kind of explained it. So, what you do is you have W equals UL minus 1 U1. So, what you do is you take U1 prime. So, this W prime is going to be UL plus 1 prime UL prime up to U1 prime, where you will write row insertion of U1 of A into U1 is A1 comma U1 prime. So, this A1 could be empty or it could be something that is bumped out. Then, so if this is empty, the process will stop here, but if it is non-empty, then you would write this. If it is empty, you think of this as, nothing is being inserted. Can you see this actually? It is too low. It is okay. And so on. So, what you will do is to define you take UL and insert AL minus 1. And that will give you AL UL prime. So, I start with U1, I insert A into it, maybe something gets bumped out, I insert that into the next row, maybe something gets bumped out, and so on, all the way up to the Lth row. And then this UL plus 1 prime is AL. If this is empty, then the L plus first row is empty. So, this is called Schensted's insertion algorithm. So, what does it do? It takes as input a word and it returns a tableau. No, actually it takes as input a word and a letter and it takes as input a tableau and a letter and it returns another tableau. Yeah, plenty. So, I'll just. So, firstly I have not even proved that it is a tableau. So, claim is if W belongs to tab lambda a n, then W prime belongs to tab mu a n for some mu belonging to lambda plus. So, let me explain what lambda plus is. So, lambda plus is the set of all partitions so suppose lambda is mu such that the Young diagram of mu is obtained by adding a single box to y lambda. Let us look at an example. Suppose we take lambda equals 6, 5, 3, 3. Then where can I add boxes to this? Well, I could add a box here, or I could add a box here, or I could add a box here, or I could add a box here. Right. So, what we get is 6, 5, 3, 3 plus is a set of all partitions 7, 5, 3, 3, 6, 6, 3, 3, 6, 5, 4, 3 and 6, 5, 3, 3. Okay, and moreover, this process W comma A goes to this insertion gives rise to a bijection. So, I am continuing the theorem, this is sort of a parenthetical definition and example. Gives rise to a bijection from tab lambda a n to union over all mu in lambda plus, maybe I should write it on the next page. Gives rise to a bijection from tab lambda a n to union mu belongs to lambda plus tab a n. So, I am going to show that this is a bijection by showing you how to reverse it. But first I have to prove that what I actually get is Tableau, right. So, this theorem needs to oh sorry, yeah, cross AN, that's a bijection. You also vary the A's. So, depending on which A you put in, the shape can change. That clear? So, what I need to do is firstly I need to show that the left hand side maps into the right hand side, and then I will construct an inverse. So, so let us just look at an example. So, let us take this Tableau to just understand how the proof works. And let us say I want to insert into this 2. So, what will I do? I will first try to insert this 2 into this first row, right. What will it displace? It will displace the 3. So, this will get displaced and this will become a 2. And now, I will try to put this 3 into the second row. What will it displace? It will displace this 4. So, this will become a 3, right, and this 4 will come to rest here. So, the principle is that if you look at this path of things, so firstly let us observe that you always display something that is, so what was the example? We had a 3, so you always display something that is strictly greater than you, right. A will display something that is strictly greater than A. And so, what we will start off with is A, and then we will have something greater than A, and then that something greater than that, and so on. So, this sequence of things that get bumped out will be strictly increasing, right. And the position from which, so what is the problem that could happen? The problem that could happen is I take something and put it here, and then what happens is maybe this this row is going to still be weakly increasing. That is not an issue, that is how row insertion works, it always gives rise to a new row. The issue could be that the column may not be increasing. So, I just need to make sure that the column is increasing. So, now of course, this number here has been replaced by something smaller. So, there is not going to be a problem at this stage. What I have here will be strictly less than what I have here. Now, the question is, when I put this, then what happens? Then some number here may be replaced by something smaller, right, because I am inserting something. So, could it disturb this order here? That is the question, but the answer is no, because this replacement will cannot occur to the right of this original displacement. So, the column numbers of bumped cells weakly decrease. Why is that? So, so I am displacing the first guy that is greater than or equal to the number I have, right, and now these numbers are actually going up. Let us see, so strictly greater than. So, right, I am running out of time. So, So, maybe I'll finish this proof next time, but the point is that, well, maybe we can do it. I think this is best done, you do it yourself in the tutorial. Okay. So, what you have to prove is that the result of this insertion is again a semi-standard Young tableau, and I will show you next time how to reverse this process. So, basically what you would do is you would notice that a new cell has been added somewhere. In this case, it has been added here, and so you need to remove this element, and then you have to guess where it was bumped up from, and then guess where it was bumped up from, and then you get the thing back. But a nice corollary of this is what is called, what I will call baby Peary's rule, which tells you what the product of a Schur function with E1 is. So, we will come to that next time. I will stop here.